Welcome to the second tutorial session in the course Basics of Mechanical Engineering 1. We have discussed about the units and dimensions, scalar and vector quantity in the first tutorial session. In this session, I will try to cover the tutorials on the topics discussed in the week 1, 2 and 3, which is friction, lubrication. I will talk about some of the numerical problems on moment of inertia and gravity. I am Dr. Amandeep Singh Oberoi from Indian Institute of Technology, Kanpur. Let us try to recall the concepts that we went through in the week 2, that is friction, lubrication, moment of inertia and gravity. We understood that the normal force N is equal to minus of F into G, which is minus of mass into the acceleration due to gravity. Friction force F acting on the object is given using the frictional force, and the friction force is given as F is equal to minus mu mg, where mu is the coefficient of friction, m is the mass of the object and g is gravity of the earth, that is acceleration due to gravity. Coefficient of friction therefore turns to be mu is equal to F by N, that is frictional force over the normal force acting on an object. We will see certain examples and we will try to understand this further using the solving of the examples. Now, only when we have a condition of impending sliding, we can also use the friction equation, that is Fs is equal to nu s by n. Along with the concept of friction, we need to understand something known as angle of repose. If there is a body that is sliding over a slant surface with a slant angle of theta and the normal force acting on the body from the bottom is N, frictional force that is acting on the body F is determined here. So, maximum inclination angle here is theta, at which body can rest on an inclined plane without sliding down, is called angle of repose. So, if it is at angle theta, it will stay here. Anything more than theta, that is, suppose if it is theta 1 more than the given angle theta, it will start sliding. But at angle theta or till the angle theta, it does not slide. So, it rests without sliding. This is known as angle of repose. As theta increases, the block remains in static equilibrium until it reaches its critical angle, at which point it begins to slide. Theta is the initial angle at which the block is at rest. So, tan theta is equal to F by N, where F is the frictional force, N is the normal force acting at the bottom in the direction normal to the base surface of the object. If phi is the angle at which the block is about to move, frictional force will be limiting friction and hence tan phi is equal to F by N, that is equal to nu, that is also equal to tan alpha. Here phi is equal to alpha, thus angle of repose is same as angle of limiting friction, right. So, I talked about angle of friction, I talked about angle of repose. Let us now try to see some examples on friction and moment of inertia. So, here is one problem statement where a person weighing 175 pound is standing on a 10 feet ladder weighing 25 pound as shown in figure. I will draw a figure here. This is a ladder that is 10 feet long and a person is standing here who is weighing 175 pound. Determine the maximum height at which ladder would be on verge or slipping fall. So, this is given in the figure only that this angle is 50 degrees, right, and person is standing, let me say, at a height h. So, let me say these points as A and B. So, this is a ladder the way it is shown. Now, this is a height h, and if I say the forces which are acting, force acting in the horizontal direction on the point A is F A, in the normal it is N A. For the point B, the force N B here is, and the frictional force is F B. Now, it is given that 25 pound is the weight of the ladder. So, weight of the ladder should be there. I will be considering this is total 10 feet ladder. So, at 5 feet length, at 5 feet length, there is a weight that is acting 25 pounds. Now, we begin by drawing a free body diagram here, writing equilibrium equations. So, we note that the friction force at each surface of contact is shown in the opposite direction to that of impending motion. So, this is very important, as we will be using friction equation along with those of equilibrium systems here. So, we say for Fx in x direction, all the forces are equal, which means Nb, which is in negative direction, opposite direction. So, I put minus Nb plus Fa, this is equal to 0. Then forces in y direction are equal to 0, which means Na plus Fb, the same direction, minus 175, the load of the person, minus the weight of the ladder, is equal to 0. And movements here are also 0. That is, summation of all the movements around A are 0. So, which means minus 25 into 5 cos 50 degrees, this is first movement, minus for the person it is 175 mass into h by 1050 plus force B into 10 cos 50, the length of the ladder is 10, plus Nb, again the length of ladder is 10 feet here, into sin 50, this is equal to 0. So, I have gotten now the equilibrium equations. So, using these equations, I will now try to get the solution based upon the given friction values. I will try to see what are the final solutions. Now, I will try to substitute the friction equation into force equilibrium equations. So, this friction equation will be put into force equilibrium equations. In two equations and two unknowns are there. One is Na and Nb. These are the unknowns, right. So, we will try to find the magnitudes of the normal forces, and these are independent of the height h. Magnitudes are independent, directions are those dependent. So, we are interested in examining different values for the coefficient of friction. So, we also know now here, I will take another space in the next slide, we will see Nb plus nu A Na is equal to 0. There is minus Nb plus nu A Na is equal to 0, and Na plus nu B Nb minus 175 minus 25, this is in y direction, is equal to 0. So, I am substituting Fa and Fb with their friction value. Fa, as we know, because nu A would be Fa by Na. So, Fa is nu into Na, that is being substituted here. So, therefore, Na is equal to nu A into Fa. This is being substituted here. Similarly, I will substitute here as well for Fb. Okay, in moment equilibrium equation as well, that is the third equation here. So, here also I will substitute the value of Fb. So, Fb I will have to substitute, this is minus 25 5 cos 50 degrees minus 175 h by tan 50 degrees plus, here is the substitution of Fb, that is nu b into Nb into length cos 50 degrees plus Nb into tan sin 50 degrees, this is equal to 0. So, equations I would say 1, 2 and 3 have given the equations 5, 6 and 7 while substituting the value of Fb as nu b into Nb and for Fa as nu into Na respectively. Now, for the three values of nu A is equal to nu b is equal to 0.3, then nu A is 0.3, nu b is 0.15, nu A is 0.15, nu b is 0.3. I leave it to you, you try to solve these problems A, B and C while giving this value, problem A, problem B and problem C. I am just giving you the solutions for while putting all these values, I get the value Na is equal to 183.49 pounds and Nb is equal to 55.05 pounds, right. And for the given values of the coefficients of friction here, nu A is 0.3, nu B is 0.15, the values of the normal forces calculated here are 191.39 pounds and 57.43 pounds for Na and B respectively. And for the third equation, for the third problem, that is nu A is 0.15, nu B is 0.3, the value of Na gotten is 191.39 pounds and for Nb that is gotten is 28.71 pounds. And for the first one, we got the value of h, height at which the person is standing is h is equal to 3.05 feet. Here h is equal to 2.83 feet and here the value of h is 1.33 feet. So, this is a solution on the friction problem statements at a stretch. So, we substitute the values using the static friction relation, that is nu is equal to F by N. We substitute those values, we use the laws of the equilibrium of the motion, the forces in x direction were equilibrium, the forces in y direction were in equilibrium, the movements were in equilibrium. So, this is these three equations helps us to find the final solution. So, there could be multiple problems that could be solved in this way as well. So, there is another problem that I could see, a mass of 50 kg is placed on an inclined plane with an angle of 30 degrees. The coefficient of kinetic friction between the mass and the plane is 0.2. Calculate the force required to move the mass up the plane. So, this is again angle of repose is given, either you increase the angle or you try to find the force at which this could be pulled up. So, it is trying to pull up or it is trying to move mass up the plane. So, that means G will come into the existence here. So, here we have been given is mass is equal to 50 kg, and we have been given theta is equal to 30 degrees, and nu k is 0.2. So, we know that n is equal to mg cos theta. If we calculate this, this is equal to mass 50 into 9.81 into cos of 30 degrees, which is equal to 424.1 Newton. Also, frictional force Fk is equal to nu k into n, which is equal to 0.2 into the value of n that we have determined here, 424.1. This is equal to 84.82 Newton. Now, force due to gravity along the side of the plane, if I try to say Fg, this is force due to gravity. I would say force due to gravity. Force due to gravity Fg is equal to mg sin theta, which is equal to 50 into 9.81 into sin 30 degrees. This value comes to be equal to 245.25 Newton of the force. So, total force that is required to move the mass up the plane is equal to Fk, that is frictional force, plus force due to gravity Fg. This is equal to 84.82 plus 245.25, which is 330.07 Newton. So, these were some problems on the friction, and also I tried to include the gravity into it. Now, let us now try to see the moment of inertia. Though I have calculated the moments in the previous numerical as well, let us try to recall the relations which were given in the moment of inertia in the theory. So, since the moment of inertia of a point mass is defined by I is equal to mr square, where m is mass of the body, r is distance from the axis. The moment of inertia of the total body to cover the entire mass is given by I is equal to integral of di, that is integral of r square dm, where dm is elemental mass of the body and r is the distance from the axis. If suppose moment is to be taken around one axis, this distance, if the moment some mass is there, small mass is there, suppose this is here, this is mass of the body around this axis and this is the distance here. So, here we determine the moment here. So, the units of mass of moment of inertia are kg meter square. The relationship between the radius of gyration and moment of inertia is expressed in the formula often found in textbooks, that is I is equal to m k square, where k is my radius of gyration, it is given here, k is radius of gyration, I is moment of inertia, m is the total mass of the object. Let us try to look at certain problem statements on this and try to have a solution on them. A hollow sphere of 40 centimeter auto dia and 30 centimeter internal dia is made of cast iron. Determine the moment of inertia and radius of gyration. That is, I have to find value of m, question mark, I have to find the value of k, that is question mark, of the hollow sphere with respect to the diametral axis. Take density of cast iron as 7860 kg per meter cube. So, there is the larger sphere, there is a smaller sphere, larger sphere is the outer dia, smaller sphere is the internal dia. So, there is a hollow sphere, we have internal dia and the external dia. Let us try to solve for both of them and then we will try to see what is the moment of inertia here. Now, for the larger sphere, let me say first. So, for the bigger sphere, I would like to know its mass. I will say mass of bigger spheres mb is equal to its density into its volume. Density is given 7860 kg per meter cube, right, and its volume should be 4 by 3 pi r square, pi into r, that is radius of the sphere would be, it is 40 centimeters. 40 centimeters means the radius is 20 centimeters. 20 centimeter means it is equal to 20 by 100, that is 0.2 meter. This is radius. I will say r of b, bigger sphere. So this is 0.2 cube. So because these units are in meter cube here for the density, that is why I am converting the centimeters into meters here. So this is mass I have gotten here is 263.3 kg. For the smaller sphere, the mass of smaller sphere is equal to rho into volume of smaller sphere. The volume of smaller sphere again would be taken using the same relationship. I have the density into its volume by r cube. Here r is 15 centimeter. I have r of smaller sphere, which is equal to 0.15 meter. So this is 0.15 meter cube. So I have gotten this mass as 111.11 kg. So what is the rationale of taking this mass? Because I need to understand the moment of inertia of the solid, moment of inertia of a sphere. There are different relations which are determined or which are already given. For example, moment of inertia for sphere MOI, that is I for sphere is equal to 2 by 5 of mr sphere. We have the hollow sphere here. We know the mass of the bigger sphere, we know the mass of the smaller sphere. We know the radius of the bigger sphere, we know the radius of the smaller sphere. So moment of inertia for the resultant body, that is bigger sphere minus smaller sphere, has to be taken. So I would put it here MOI for or of the resultant body is equal to, that is moment of inertia for the bigger sphere minus moment of inertia for the smaller sphere, which is equal to 2 by 5 into mass of bigger sphere into radius of bigger sphere square minus 2 by 5 into mass of smaller sphere into radius of smaller sphere square, which is equal to 2 by 5 into 263, that is mass of bigger sphere taken from here, into 0.2 square minus 2 by 5 of 111.11 into 0.15 square. This is equal to 3.21 kg meter square. So this is moment of inertia. The first part is over. Now the second part is radius of gyration. So recall the relation I is equal to mk square. M is the total mass of the object. So to find radius of gyration, as we know, radius of gyration, we know I is equal to m k square, which gives me k is equal to I by m under root. This is equal to, the value of I is given here 3.21, and mass of the body is the difference of the mass of the bigger sphere and the smaller sphere, that is 263.3 minus 111.11 under root of this. This radius of gyrations turns out to be 0.14 meter, which is equal to 14 centimeters. So, this was one problem to calculate the moment of inertia, the radius of gyration, and we tried to calculate it. So, there is another problem statement where two circular discs of radius 10 centimeter and thickness 4 centimeter, radius 10 centimeter, thickness 4 centimeter. These are made of steel. These are attached to two ends of an aluminum rod of radius 4 centimeter. The length of the aluminum rod is 60 centimeter. Find the moment of inertia about the axis of rotation. Assume the density of aluminum as 2710 kg per meter cube, and for steel it is 7860 kg per meter cube. This is a problem for your home practice. You will find the solution in the lecture notes. I will give you the lecture notes a week later, and these problems you will try to solve. You can also make a diagram that how are these bodies being connected here, and how do we have the circular disc of the given radius and thickness, and the density also is given for aluminum and steel. Try to solve it and you try to get the solution. With this, I am also ending the first part of the tutorial 2, where I have discussed the friction, the gravity, the moment of inertia related practice questions. I will now try to come to the second part of the second tutorial session, where I will try to talk about the stress, strain, residual stresses, Poisson ratio. All these parts will be discussed in the second part. Thank you.